Hello, welcome to ZK Whiteboard Sessions. We're doing a module today on RISC-V zkVMs. I'm Tracy. I'm here today with Uma. I'm the co-founder of a company called Pluto, and we're building cryptography tools for devs. And Uma is the co-founder of Succinct, which is building zkVM. So we're going to dive into some of the details of how zkVMs work and hopefully explain them. Uma, you want to start us out maybe with an introduction to zkVMs and what they're good for?
Yeah, for sure. So maybe we can start off by talking about what does zkVM stand for. It stands for Zero Knowledge Virtual Machine. And what that means is that if you are used to a previous era of ZK, typically you would write a circuit for your computation, where basically you take your computation or function that you want to generate a ZK proof of, and you write a fixed computational graph for it that a lot of people call circuits. In a zkVM, you have a program, you compile it to some ISA, instruction set, and then you prove the execution of that instruction set. So you have a circuit that proves the execution, in our case, of a RISC-V ISA, and then you prove programs that are compiled to that ISA instead of circuits.
Got it. And so that's easier than writing a circuit?
Yeah, so the main point of zkVMs is that writing a circuit is very difficult. It's very annoying. With a zkVM, you can just write a program in a normal programming language or a ZK-specific programming language, and then you don't have to write a circuit. The zkVM just takes care of all the ZK stuff for you.
Got it. Cool. Maybe we could get into, I guess, like a high-level overview of like the core pieces of it and how they work together.
Yeah, so the general pipeline of a RISC-V zkVM, in our case, is we take normal Rust code. So you have Rust here, and you just have totally normal Rust code. So for example, you can have like for, and this is going to be some pseudocode. Maybe I just compute like
the sum or something.
Yeah, the sum. And then basically, so we have some normal code, and then it gets compiled to RISC-V. So RISC-V stands for Reduced Instruction Set. It's a small open source instruction set with a very small number of instructions. That's why it's called reduced. I believe it's like maybe in the around 30 or 40 instructions, something like that. And it's a standard target of the Rust compiler. So you don't need to do anything to the compiler. It's a standard supported target. A lot of people use it for like other applications other than zkVM, so like embedded devices and things like that. So we just have normal code. We use the regular Rust compiler, and then we get a bunch of RISC-V bytecode. So your program over here turns into something called an ELF. And the ELF is basically like the series of RISC-V instructions that your program gets compiled into. And so, for example, you could have a really simple program, and I'm just going to have like a few instructions here. So for example, one of the standard instructions is like add, and in this case, add I stands for add immediate. RISC-V has this notion of registers, where you have, I believe, 30-something registers, and each register, generally instructions operate over registers, so you might have something like this, where I'm going to add, or let's do actually something like this. I'm going to add the value in the 0th register, x0. I'm going to add the constant 5, and then I'm going to store it in the 29th register. So that's kind of what this instruction represents. So I might do that again.
And all of these concepts, these are all traditional computer science concepts.
Yeah,
right?
yeah. There's nothing ZK specific going on here. No. And then maybe I'll and the values in the 29th and 30th register, and then put it in like the 27th register. So for example, you might have instructions that look like this. And this is all contained in your ELF file. So that's like the, kind of a representation of your program in terms of these RISC-V instructions. And then once you have your program.
And normally, I guess, this is meant to be run on a CPU. So
Yeah.
like this is a file for a CPU, and then you're going to do something special with this file.
Yeah, exactly. Then we have our zkVM, which basically is going to prove that when you run this program with the specific set of inputs, that it results in a particular output. And so in our case, we take the ELF, we run it through a zkVM, and out we get a proof.
Awesome. Okay, this looks good. So this is maybe like not the classic CPU instruction set, right? Normally when you make a Rust program, you don't get this. You get like x86 or something, and here you're using this special instruction set, which is maybe a little easier to use when generating the proof. Cool, I think this makes sense to me. And so maybe we should dive into like, what does it take to make a proof and an example of a proof?
Yeah, sounds good. So the compilation part is actually very easy because we're using this like standard compilation target.
Do you have
Rust.
to make any modifications to it? It's really just run Rust with a target's flag.
You basically just run Rust with the target flag.
That's cool.
So yeah, once we have our ELF, then we actually have to do all the ZK stuff. Okay, so maybe we can dive into how that works. So we have an ELF that has like the instructions. So let's go back to that world. So the first thing we do when we have this ELF and this program is we execute it. So we have some sort of runtime, like we have a RISC-V emulator. So we have a runtime /emulator. And we actually just execute the ELF, and we execute each of the instructions. One important thing to understand here is one question you might ask is, well, how do we know which instruction to execute? So you have a start program counter. So you have this notion of a program counter, which tells you which instruction in the ELF you should actually execute. And the program counter is literally just a number, and then you use that number to index into your ELF, which is just a list of instructions. So it's really simple. You index into this list, you grab an instruction, and then you execute the instruction. And so first you do execution with this like emulator. So there's the execution phase. And that's dictated by the start program counter. Then you basically have a while loop that will get the latest instruction. So it'll fetch the instruction, and then it'll execute the instruction, depending on what it is. And then at the end, there's a halt instruction, or there's a way to signal that the program is terminated. So you generally call like halt with some exit code, and then that's when the program stops. So you might ask, okay, given a particular opcode or instruction that I'm executing, how do I figure out what's the next instruction to execute? Typically, for example, for add instructions, you just increment the program counter and execute the next instruction. But sometimes there's things like jump. So for example, the JAL opcode stands for jump and link. So this happens in like for loops and function calls and in general, any logic that is branching. And that will actually increment the program counter to not go to the next instruction, but go to another place in the code. And so you have jump instructions, branching instructions that explicitly modify the program counter to go to a specific place in the code and not just execute the next instruction. And that's how we get function calls and if statements and for loops and things like that.
Got it. So the goal of this emulator is to kind of do what a normal CPU would be doing if it was executing this ELF file, but mix the ELF file with maybe a specific input, and then based on that, give you like an execution trace, something like this.
Yeah, so actually the way inputs work in our program is that we have this concept of syscalls. So typically, even in like normal programs, often it's a question you might ask is, okay, how do we get the arguments to the program? How do we get the input to the program? So for example, if I'm trying to prove the nth Fibonacci number, how do I know what n is? For us, and also in RISC-V, the opcode, which is like what operation is this instruction running, is called ecall. And this is a syscall. And generally, these ecalls are used to talk to your host environment. So your ecall, in typical programs, it's used to talk to the kernel or do other things. Here, we use it to get inputs and also write outputs. So this is used to get inputs and outputs and do a bunch of other stuff. It's basically you can think of it as special instruction. So to get inputs into a program, we just call ecall with a particular syscall code. So there's just some constant that says, hey, at this point we're reading input. And then what that will do in our particular zkVM is it'll just read input that the runtime is instantiated with, and it'll start loading it into registers and memory. So that's how input and output kind of work in our zkVM.
And maybe, yeah, so, okay, this makes sense to me. You're kind of working through this program one instruction at a time, and you're probably logging something along the way that's building up what should be a witness for your proof, I'm guessing. So what does maybe an example of a witness look like, or some execution trace? And then maybe we can start diving into the actual proof.
Yeah, totally. So yeah, maybe this is a good time to start talking about how a zkVM generally works, at least in the current paradigm. So in general, I think most zkVMs today are using SNARKs, fry, and error arithmetization. And so in that world, basically what you have is you have some sort of table. So maybe you have the CPU table. And the goal of this SNARK is to constrain that your program is executed correctly. So each row corresponds to an instruction. And so here, for example, let's do the add instruction. You'd have the opcode. You'd have the operands. So in this case, it would be add. Now, obviously, this is replaced with a number, a const that it corresponds to add. You'd have the operands. So in this case, it'd be 29, 0, and 5. So in this case, the 29 is a register. This is a register. This is a constant. And then you would also have the program counter. And then there's a bunch of other columns for other stuff. And really what's happening underneath the hood is that each instruction gets turned into one row in our SNARK. And then we want to prove that the instruction was executed properly. So what does that involve? First, you have to check that the program counter was updated properly. And so, for example, in the case of an add opcode, it's very simple. You just increment the program counter by 1. But in the case of, for example, a jump and link instruction or a branch instruction, you have to have more intricate logic for checking that the program counter was incremented properly or set properly to the next program counter.
Got it. And so some of these checks probably have to look at what happened to the registries, what happened to the memory. Maybe, is there a memory piece to this as well?
Yeah, that's a bit more complicated, and maybe we can dive into that in a little bit.
Okay.
So yeah, basically you check that the program counter was updated properly. You also have to check that the memory and registers are set correctly. Mm-hmm. And then you also have to constrain the actual operation. So you have to constrain the actual particular opcode. So for example, in our case, and maybe I'll go into a little more detail here. For example, for an add instruction, you have the operands, and then you kind of have the quote unquote values. So for example, this is a register. So these are both registers. Register, constant. It's probably a bit hard to read. I'm just gonna erase it. And then, so when you have a register, you also have to like, take that register and look up what is actually the value at that register. So in our case, maybe imagine all our registers are set to 0 at that point in time. So x0 is 0, 5 is just a constant, it's 5. And then after you add the value in x0 and the constant 5, x29, register 29, should be set to 5. And so if you look at these values, we do a memory argument basically to show that, or we have to constrain that after you run this instruction, the 29th register has a value of 5.
And so the goal of this procedure is to sort of show that the machine is transitioning correctly through each of these states and not violating any sort of rules about how memory can be updated or the order that memory is touched and updated, etc.
Yeah. And one interesting detail is that in our proof system, and in general, I think most VMs operate over small fields these days. So maybe you can talk a little bit about like the proof stack that people use.
Yeah, so in this CPU table, like these aren't necessarily integers. They're like all field elements, right?
Yeah, so the proof stack most zkVMs use is SNARKs and Fry. And then they usually use a small field. So for example, Mersenne 31 or Baby Bear, these are both they're 32-bit primes, or I guess 31-bit primes.
What does that mean, small field?
Small field. So in general, like when you do Starks and Fry, you can have a choice of like what prime field you're using in these like proof systems. Historically, people have used like bigger fields. So like, 250 fields that are like 251 bits, 252 bits. And in like the old world of SNARKs, you have to use those big fields. However, I guess maybe not recently, but in the past few years, it's become very popular to use much smaller fields in proof systems in general. And the reason for that is small fields are really hardware friendly. So because this field is less than 32 bits, it can fit into one word, and therefore your arithmetic gets a lot faster, and so your proof times get a lot faster.
Got it. So like this table, instead of being filled with really big numbers, is filled with 2 to the 32 or smaller numbers.
Yeah, exactly. So in our particular case, we use Baby Bear. I believe there's Starkware, for example, is using M31, and other teams also use Baby Bear. We use small fields, and then we can like go into the other things like what our lookup argument is and things like that. But before we do that, one thing to note, for example, here is that in RISC-V, we use RISC-V 32-bit variant. So in RISC-V, the word size is 32 bits. Now, our field is actually smaller than 2 to the 32, and so we can't keep all the RISC-V values just as one field element because it'll overflow our field. So what we end up doing actually is these values, I kind of lied before or simplified before. These values actually are all represented underneath the hood as 4 field elements. So you'll have values here, and there'll be 4 field elements that represent each value. So for example, 5 would be 5, 0, 0, 0. Here it'd be 0, 0, 0, 0 to represent 0, etc.
And this is just because you can't pack the 32-bit size from RISC-32 into the field element of Baby Bear or M31.
Yeah, exactly.
Got it.
And so then, for example, now it becomes a bit more difficult because to constrain an addition, you have to basically do grade school arithmetic. You have to write an error to constrain addition. So you have to prove that, when you add these two 32-bit things together, it results in this 32-bit thing. There's like a lot of that's like a very standard thing to do. And so, you often have to have extra witness columns to constrain that appropriately and stuff like that.
Right. So instead of having just like one constraint, you have like several
Yeah.
constraints. You have to check a few more conditions. But
Yeah.
I think that makes sense. And then you have to do that for every single instruction.
Yeah.
So it does increase the cost, I guess, of doing this a little bit, but it's sort of what you have to do.
Yeah. So for every single opcode, you have to basically figure out what are the constraints, like what's the error arithmetization, and what are the constraints I need to constrain appropriately the logic of that opcode. Most opcodes have like fundamentally very similar high-level flavor. You have 3 operands. Some of them can be immediates, which means it's a constant, not a register. But if it's not a constant, it usually involves reading a value from a register. So yeah, most operands, you load registers if appropriate, or immediates. Then you do some like arithmetic with them. So for example, add is adding the 2 operands and then storing it in the destination operand, and would do the same thing, or XOR. So there's a bunch of like ALU, we call them operations that are just doing like arithmetic. Then there's a class of operands that involve dealing with memory, so like loading and storing to memory. So that will read from memory and put it in a register, or take a register and write it to memory. Then there's branching operands that basically, check if a particular value in a register is equal to something, greater than something, less than something, and then increment the program counter appropriately. And then the jump instructions also do something kind of similar, but most of the time they're just touching the program counter. So I think those are like most of flavors of the instructions. But yeah, most instructions involve registers and like constraining values from registers and then doing some logic on top of that.
Are there specific instructions that are like really hard?
Yeah, so RISC-V was obviously not designed for being proven in a zkVM. And so they often have pretty annoying instructions. Like, I think the multiplication, so we actually prove a extension of RISC-V. There's a base RISC-V 32 variant that doesn't have multiplication instructions. We prove RISC-V 32 IM that has multiplication instructions. Some of those can be really annoying. Because you have to multiply a word by a half word, or you have to multiply unsigned by signed, and then you have to do a lot of annoying logic with, detecting what is the top bit of a particular, result and things like that. So those can be pretty annoying.
Cool. All right, yeah. Maybe we'll dive into the internals of this now and how sort of memory attaches to the CPU and some of that. All right, so cool. This explains the CPU super well. I guess there's also like memory and some other pieces. Are those all represented in this one big thing, or how do those kind of fit together?
Yeah, for sure. So let's maybe first introduce or talk a little bit about the concept of lookups. So I'll put it here.
Oh, sure.
So in general, SNARKs are really good. You have like this one table, and it has a bunch of constraints, and it's proving the program counter was updated correctly. The opcodes are, actually being constrained. Like the values have the correct properties. They're being added together, ANDed together, XORed together, whatever. But actually, that's like kind of a simplification of what's going on. In practice, we don't just have one SNARK for a CPU. We actually have many, many SNARKs that talk to each other via lookups. And in particular, we use the log derivative lookup argument to do that. And at a high level, what a lookup allows you to do is it allows you to have certain columns in one table basically talk to certain other columns in another table and say, these columns here appear in another table. So why is that useful? I can draw it out. So in practice, we don't just have a CPU table. We actually have many tables. So for example, we have an add table. We have a and table. We have a like mul table. We have a shift table.
So you have one for every instruction, pretty much.
We have tables for most instructions, and or at least for the arithmetic instructions.
Oh, I see.
And what happens is, and this is pretty specific to SP1, succinct zkVMs, the succinct zkVMs architecture. So, other zkVMs make different design decisions. We have this multi-table architecture, and what happens is the CPU is actually really lazy, And it doesn't do that much. It just takes an instruction. It makes sure it loads the values. So it makes sure that like all the registers are loaded appropriately. And then what happens, for example, for an add instruction is it just looks up that A, B, and C, which are the 3 operands, appear in the add table. And then the add table is responsible for constraining that B plus C is equal to A.
So you can put kind of or like instruction-specific constraints here, and then this thing can kind of be naive. It just has to think about what a CPU needs to do. It doesn't really care what the instruction specifically does.
Yeah, exactly. And so this is kind of like a very lookup-centric architecture where the CPU is just looking up the result of the operation. And why is that really nice? It's nice because in practice, to constrain that A equals B plus C, you actually need some extra columns over here. So you need extra witness columns. And these witness columns are usually for things like carries or stuff like that.
And this is probably variable, like different instructions need more witness, some need just a little bit.
Yes, exactly. So the add table, for example, is pretty simple. Like adding stuff is pretty simple. Earlier, we had kind of talked about the mul table being really annoying and the mul constraints being annoying. So the mul table has a lot of witnesses and a lot of edge cases, and it's very complicated. Now, if we were to try to do this all in the CPU, what we would have to do is we'd have to have all the witness data in the CPU all the time. And that's kind of bad because we'd have to have all this extra area in the CPU, which, for example, when we're doing an add instruction, we don't need all that extra witness data that we might need for a multiplication instruction. So we're kind of paying for all those columns and all that trace area, even though it's not being used. With this lookup-centric architecture, we don't pay for any witness data or trace area that we're not using. So it's much, much more efficient than trying to stuff everything in one table.
Cool. This is actually like a pretty subtle innovation, if I remember correctly, because like these end up becoming different proofs, isn't that right? Like this is one STARK, this is another STARK, this is another STARK. Is that how this works?
Yeah, so this ends up being one STARK, this is one STARK, and then another STARK.
I see.
And then the lookup argument just makes sure all the STARKs are connected together appropriately.
Got it. Okay. Do you have to then like somehow aggregate these STARKs together or recursively verify them or something?
Yeah, so if you have a bunch of these STARKs, in practice, what you have to do to get like one final STARK is you recursively, you have a few options. One is you could just have a bunch of these STARKs, and it's still a constant size proof. So you could just have a bunch of STARKs, and your proof is just a little bigger. You could also recursively aggregate them using STARK recursion, where you verify a bunch of proofs in another proof to get like one final small STARK. And in practice, we do that also for proving larger programs, which I think we'll talk about in a little bit.
Maybe this is interesting to talk about too, but I think when I learned about lookups, I was thinking about them as like a single proof. But here you're actually doing a lookup across proofs. Does that introduce complexity?
Not for our lookup, using the log derivative lookup argument, not really.
Okay.
Yeah, you can also do lookups within a single proof as well. For us, it's not that much extra complexity.
Got it. Okay, cool. So you have these instructions, you have a CPU. Is there anything else here?
Yeah, so maybe another interesting thing to dive into is our memory argument. So actually, how does loading all these values actually work? Maybe you can talk about that. So memory obviously is a big part of a VM. And there's been several different techniques for doing memory within zkVMs. So the older technique is known as Merkleized memory. Basically, how that works is you have memory. So you just have like a bunch of addresses in address space. So you'll have like, for example, address 0 has this value, address 1 has this value, and then, you'll have some big address space. So maybe it's like 2 to the 32 has this value. And then what you do is you commit to the memory. So you basically construct a Merkle tree of all these address value pairs, and then you get a Merkle root. and that is a commitment to your memory. Now, every time you access a memory address in your zkVM with Merkleized memory, you first prove that you're accessing the particular value against the Merkle root. So you have some current Merkle root that says this is the memory. You open. So when you do a memory access, you first open with the Merkle proof.
So I guess maybe briefly, just to add context, like the goal here is to kind of put some structure to the memory and share it with the CPU or the other STARKs that are a part of this so that they can, similar to what you do with the instructions, like look into this thing and make sure it's in the correct state.
Yeah, exactly. Because like, for example, each instruction is generally modifying memory or registers. In our case, there's no real distinction between memory and registers. Like registers are just, we just think of it as like other addresses in memory.
And this varies over time too, right? So like you might have this entire snapshot at time 0 and then time 1, or instruction 0, instruction 1.
Yeah, exactly. And in the zkVM, it's really important that you prove, hey, when I tell you, oh, register, 29 has this particular value, that is actually true. Because obviously, if you could claim that a register has a particular value and that's not like a provable fact, then your entire program execution is totally meaningless.
Got it. And then there's a lot of different ways you can represent this, and one is this Merkle thing.
Yeah.
And I guess you're about to share how to pull data out of it. Yeah.
Yeah, exactly. So you basically commit to your memory. You say, hey, here's a Merkle root that's like a succinct commitment to all my memory. And then when I want to access a particular value of memory or a particular address, I open the Merkle proof. So I verify a Merkle proof against this Merkle root. Then I do whatever logic, and then I'll update the Merkle root. So if it's a read, I don't have to do the second step. But if it's a write, then I have to obviously update the Merkle root with the new value. Obviously, this is kind of undesirable because it introduces this log n, where n is like the size of your address space, overhead to every access to memory. And so this was kind of a older technique, but the technique that we use is a newer technique. It's known as offline memory checking. And it makes use of our lookup argument. So what we do in our memory technique, in our zkVM SP1, is when we access memory at a particular address and it has a particular value, we have this notion of a timestamp, which is basically kind of like the clock cycle of when the instruction is getting executed. And the clock cycle is just strictly incrementing throughout the course of our program. So for example, the program counter does not have this property because it can like jump around your elf, but the clock cycle, no matter what, each instruction always increments by 1, or roughly that. So for us, this clock cycle, or what we call timestamp, is a strictly incrementing thing throughout the course of our program. And whenever we access a particular memory address and want to claim that it has some value, what we do is we add to our log derivative lookup argument the tuple, and this is kind of like assuming that you know about the log derivative lookup argument. You add this tuple of address, the current value, and the timestamp to the lookup arguments accumulator with multiplicity +1. And you add the address, the previous value, and the previous timestamp that you last accessed that memory with multiplicity -1. And then at the end, if you do this for every single access, each of these will cancel out, and then you will have to check that your accumulator for your memory is equal to 0. And that's how we check our memory access was all consistent. And I think it's a bit hard to see maybe from this. We can go into like a little example. But maybe before I do that, one question people might ask is, how do you constrain that an access was a read versus a write? It's actually very simple. If you want to say, hey, I accessed this memory and all I did was read it, you just say value is equal to previous value for reads. And then for writes, that's obviously just not the case because you're writing. So for example, in our CPU, for most instructions, you're generally reading from 2 operands and you're writing to the 3rd destination operand. So in that case, we access the memory at those 2 operands and we make sure that we're reading and not writing, and then we write to the 3rd operand.
I see. So this kind of lets you efficiently check the state of the VM as you're going through it without, and just almost summing them into an accumulator. And then you don't have to do Merkle paths, which are maybe a little less efficient. Okay, and then at the end, you know the CPU touched all of the memory registries in the correct order and at the correct time.
Yeah, exactly. So maybe to go through a small little example of this, to develop some better intuition for like why, you can't cheat, you can't make like a false proof. Let's imagine you're trying to access memory at some address 500, and at times, so this is the address, this is the value, and this is the timestamp. So say it were time 10, and the value is 7. And then we're at time 11, and we're also accessing it again. And now we want to do a read, so the value is still 7. And then say at timestamp 20, the value, we want to do a write. So this is a read, this is a write, and the value becomes like 15. I also forgot to mention that another really important thing here is you always have to check that the timestamp here is greater than the previous timestamp you accessed. So that's why the timestamp is important. This is like a very important check. And I'll go over why that is.
It just means it's ordered, right?
It means that your kind of log is ordered properly. So for example, here, at this point in time, and imagine that the memory address was initialized at timestamp 0. And with this argument, you have to do like a initialization phase where you basically just, for all the memory you're going to touch, you just have to add it to the accumulator at the beginning to initialize it. So it cancels out like the first read or last write or whatever. So there's some subtlety there, but so here we've basically added the tuple 500, 7, 10 with +1, and the previous value, maybe let's say was 0 at timestamp 0, so we've added -1. So this is like the initialization, and that's like kind of taken care of separately. Here, you can see that we've added 500, 7, 11 with +1, and we've added 500. The previous value was 7, and then the previous timestamp was 10 with -1. So you can see this guy here cancels this guy here, right? So those two cancel out. And then here we add 500, 15, 20 with +1, and we subtract 500. The previous value was 7, and the timestamp was 11 with -1. And you can see that this guy here cancels out this +1 here, right? And so at any point in time, for example, if I tried at this point to claim that, or say at this point I was trying to claim, I was doing a read, and I was trying to claim that the value, and I was malicious, and I was trying to pretend that the value was actually 8 or something like that, well, I would run into trouble because here I would have to have 8, 8, and then suddenly this guy does not cancel out this guy, right? So you basically run into trouble where now this thing and this thing don't cancel out, and then your accumulator is not 0. Does that kind of make sense?
I see. Yeah, it does. So you add this sort of fixed functionality into your SNARK, which does this behavior on the memory accumulator every single time an instruction is processed. And then if anything about the memory is out of sequence or doesn't have the correct value, you get to the end of this, and then it's obvious that it's incorrect because you don't have the 0.
Yeah, exactly.
Okay, that's really cool. Awesome. All right, should we talk about, let's see. So we did memory. Should we talk about precompiles maybe?
Yeah, let's do it.
All right.
So this is kind of one reason that SP1, our zkVM, is very efficient. And in general, zkVMs are awesome, right? You write normal code, it gets compiled to this normal target, RISC-V, and then you prove it. So it's kind of like, that's super awesome. Now, the downside is, it can be much less efficient than, handwriting a circuit or like a specialized circuit for your particular computation, because there's a lot of overhead in a VM, right? You're like reading and writing to memory, you're reading and writing to registers, you're doing a bunch of random operations. And so there's a lot of overhead. And so one way that you can address this overhead is through this notion of precompiles. Maybe I can kind of describe, at a high level, how you can think of it conceptually, and then we can dive into how it actually works.
And people call these different things, right? There's like
accelerators,
coprocessors, accelerators, precompile. They're all kind of the same thing, but it's like a special circuit that is more efficient than your standard CPU circuit.
Exactly. Yeah, it has a bunch of different names. So for example, for a catch-ack hash function, normally in my VM, if I just compile catch-ack to RISC-V, maybe it has 10,000 cycles. And this is kind of a hypothetical number. I think it's something around that. And so, it looks like, okay, I'm XORing a bunch of things, I'm loading a bunch of things, I'm storing a bunch of things, etc. So naively, it's just 10K cycles. So that means it's like 10K rows in my CPU table. But one interesting thing is if you have a specialized circuit for catch-ack, then you can actually, so with a precompile or a specialized circuit, you can actually have much, much less cycles. So you basically replace this 10K cycles with a specialized circuit, and it goes down to like hundreds of cycles. And so concretely, what that kind of looks like is we have our CPU here. And remember before, even I'd explained to you guys that we have this multi-table architecture where like the CPU is really lazy. For an add, it actually just looks up the add. For catch-ack, we actually do something similar. So we signal to the CPU, we want to do a catch-ack. So in practice, how that actually works, we use this like eCall, which I talked about previously, eCall or syscall instruction. And we say we're going to do a syscall with catch-ack. So we're going to do a catch-ack syscall, and we're going to pass in like to a pointer. So we pass in a pointer to the array region that we want to do catch-ack on. So we pass in a pointer, we signal we want to do a catch-ack, and then in the CPU, we load the pointer, and then what we do is we have this catch-ack table where it's responsible for doing the catch-ack. So in our case, our precompile tables directly talk to memory. So for example, here, we have the pointer, we have a timestamp, which is like the cycle that the CPU is going to look this up. And then we have a ton of columns here that are doing like XORs, that are talking to memory, that are doing ANDs, that are doing adds, like whatever you need for catch-ack. And it's kind of doing it all in one row. So basically, instead of paying like 10K cycles in the CPU and paying 10K rows over here, which is a lot.
And the CPU rows, these are really narrow, I guess. And then these are really wide, so you can lay out a lot more memory and a lot more data and operations.
Yeah.
Okay.
So normally in the CPU, our CPU, I think, is like, 100, 200 columns, something like that. We hope to make it skinnier in the future. But the CPU, so you have 10K rows here, and it's like 100, 200 columns. You replace that instead with, it's not actually one row. I think it ends up being like 32 rows or something like this, with 32 rows here. Now the catch-ack table is a lot wider. It's like 3,000 columns. But in the end, we've saved a lot of trace area because we've replaced 10K times like 200 with like 32 times 3,000. And that math ends up being like much, much better. It ends up being like an order of magnitude, basically. And so, the reason we can have these savings is that catch-ack table is really wide and it's really specialized. So it just does like XORs and ANDs and adds. And then we also basically lay out the memory. Like normally it's kind of inefficient because if you just naively compile to RISC-V, you're like loading and storing to memory all the time. You're doing a bunch of stuff. Here, we don't have any of that overhead. We can just directly take the results from the previous operation and put it into the next operation without having to talk to memory.
You don't need to like emulate what the CPU does to actually do this computation. You can just like you can just witness the computation and show that it is correct.
Yeah, exactly.
Okay.
And so this ends up being like really, really significant. Like it's kind of like an order of magnitude, sometimes more gains, because you're just proving a lot less, significantly less trace area. Like you've replaced 10,000 cycles with like hundreds of cycles. And you've replaced, a lot of trace area, so maybe like hundreds of thousands of cells with just like 1,000 cells or something like that.
Does this impact the Rust programmer?
No, this doesn't really impact the Rust programmer, because in practice what we do is you have an existing crate. So for example, there's like a tiny Ketchack crate that's a pure Rust implementation of Ketchack, or you have a Rust crypto crate that's an implementation of Ketchack. And then what happens is we fork that crate, and we maintain a fork of it that replaces like the logic where normally you would be just doing normal Ketchack stuff. We just replace it with this eCall instruction.
I see.
So we just inline the assembly, we replace it. And then from the programmer's perspective, all they have to do is they have to use our crate as a dependency instead of the normal crate. Or they can use like cargo patching to just like replace it underneath the hood.
Oh, that's cool. Awesome.
So it's really nice.
Okay, cool. Precompiles are covered. I think there's one other thing that we could cover, which is there's this idea of like long-running programs. And I've heard it called a bunch of different things, but I think the issue is if you run like a short Fibonacci, that works just fine. But when you start running like millions and millions of instructions, you start running into issues. Maybe we could talk about like how you address that problem.
Yeah, totally. So you're totally right that if you run a short program that's, maybe a few 100K cycles or even 1,000,000 cycles, we can just have one SNARK proof for it. We have like our CPU, we might have our, ALU tables like add and mul and stuff like that, maybe a few precompiles, and then, you just get your proof. But often the programs we want to prove end up being hundreds of millions, if not billions of cycles. And you can't generate a SNARK proof with 1 billion rows. You're just going to run out of memory. Like it's not actually going to work. And so for that, we have to do, you generally have to break up your program into segments or chunks. We call them shards in SP1. So you take your really long program that has a ton of instructions, you break it up into fixed size chunks of like, 1 million instructions at a time. And then you generate SNARK proofs of each chunk. And then you combine each of these SNARK proofs together using SNARK recursion to get one final SNARK proof. So maybe I can draw out a little diagram of that.
Are we done with this too?
Yeah, I think so. So yeah, basically you have, I have a really long program, let's say.
Does this also, this helps with like tons of instructions. Does this also help with parallelization?
Yes.
Okay.
So first I break it up into chunks or shards. So this is shard 1, shard 2, etc. Maybe each of these have like 1 million instructions. And then what I do, as you said, it's also really good for parallelizing the proof. I have each of my shards being proven. And one really cool thing is I can prove them in parallel. So if I have a bunch of computers on AWS or I have some cluster, I can prove each shard in parallel. And so the end-to-end latency of the proof is not like first I have to prove this shard, then this shard, etc. The latency of the proof is actually logarithmic in the number of cycles, which is really awesome. So I'm proving shard 1. I have shard 2. Shard 3, and then each of these has a proof. So this is a proof, this is a proof, this is a proof. And then, the bad part about this is now I have a bunch of proofs. So it's not that succinct, right? The whole point of a zero knowledge proof, well, there's 2 points. One is it's zero knowledge, so it's like privacy preserving. Another is that it's succinct. If I have a bunch of shards, obviously this isn't a fixed size proof with the length of my computation, and we want a fixed size proof. So what do? I basically can recursively combine 2 of these shard proofs into one proof by using SNARK recursion. So this is a concept, and it's pretty commonly used, where you make a proof that 2 other proofs are valid. Or in practice, you can also have n other proofs. So you can take a bunch of proofs, we call them child proofs or leaf proofs, and you can combine them into one proof. You do this a few times, you basically have a tree of proofs. And then at the end, you get, one final proof at the end. That's just, end up with one STARK proof.
How big are these proofs? Are these like...
They're maybe like hundreds of kilobytes.
Okay, so you have like maybe dozens or hundreds of these...
hundreds or thousands sometimes of these 100 kilobyte proofs can end up being fairly big if you're dealing with a really long computation. And at the end, you just get this, several 100 kilobyte proof.
Got it. So you could send all of these hundreds of 100 kilobyte proofs to somebody and they could use that to verify that this is correct. But instead you do these sort of like this layered thing that gets them into one even more succinct proof.
Yes. And one interesting thing to kind of talk about is recursion is very, very difficult. So you might ask, okay, how do we actually do this recursive part? Naively, one thing you could do is you could write a STARK verifier in normal Rust code. You could, basically compile it to RISC-V, and we could use our original RISC-V VM to basically verify a bunch of child proofs and then generate one proof. That's like the naive approach. Right. Unfortunately, that doesn't work. We tried it. It doesn't work. RISC-V has way too much overhead. It basically is computationally infeasible to do that. So we actually, and I think in practice many teams, have a recursion VM. So we built another VM that has its own ISA, specialized for STARK recursion. So it only has like instructions that deal with recursion, like, Poseidon hashing or like fry-fold or things like this. And then we wrote a program in that specialized instruction set to do this operation. And so we actually have a specialized recursion VM over here that is responsible for doing this recursion.
Interesting. Why does it need to be a VM versus a circuit?
It can be a VM. It could be a circuit or a VM. Sometimes having a VM is nice because you have extra flexibility. You can have like branching logic and stuff like that. If you do a circuit, you don't have those affordances. And so I think some teams do a recursion circuit. We do a recursion VM. I think in the future, we might also do a combination of circuit and VM, like circuit's more efficient when you don't need the flexibility.
Cool. That makes sense. So this is just a more efficient circuit that lets you take what are chunks of the RISC-V and combine them together into a STARK.
And you also have to, verify things like, okay, the program counter, the last program counter from here is equal to the start program counter from here. And you have to do checks like that.
You have to like link these together to make sure that they actually follow the full
Exactly, in sequence. And so, you also have to do a few checks in this recursion program that, these things are all appropriately linked together. Also for us, we kind of make use of this unique thing where globally, our memory argument is global across the entire computational trace. And so, we have to do some extra things for that. But we also have to sum the accumulator from here and here to get a summed accumulator across all these shards. And at the end, we check at 0.
Got it. Cool. That's really unique. Yeah, I guess maybe from here we can talk about, so you, at the top of this tree, you have like 100 kilobyte proof, and then typically these are being verified on chain, I guess. And so you want to somehow get that to an even more compressed proof that you could put on chain, is that right?
Yeah, so typically what we want to do with this end proof is we want to verify it on Ethereum.
Gotcha.
Obviously ZK is useful even outside of blockchain, but a really big use case for ZK is ZK rollups, where you have a bunch of transactions, you have a layer 2, you batch them together, and then you want to prove that the transactions were executed correctly, and then there's a new state root. And then what you do is you verify those proofs on Ethereum, and then that's kind of like how we're scaling Ethereum is with these ZK rollups. So a main target for us is verifying these proofs on Ethereum. Now Ethereum is very, very slow and very expensive. So it doesn't even like these proofs are pretty small, things considered. A couple 100 kilobytes is not that much. But Ethereum doesn't like that. It would cost like millions of gas to verify these proofs on Ethereum. So what do? We take these STARK proofs and we wrap them in a SNARK. So that's known as like STARK to SNARK. It's kind of like the last stage of our pipeline. We have like our core RISC-V proving. Then we have recursion with the recursion VM / circuit. And then finally we have STARK to SNARK. So it's, yeah, building a zkVM is there's a lot of moving pieces. So we have STARK, and then we take it into a SNARK. And the reason for that is Ethereum has a bunch of precompiles for the BN254 curve. So like in particular, we use these pairing-based SNARKs. And we use them with the BN254 field because the Ethereum EVM and Ethereum have precompiles for it. So it's pretty cheap to verify pairing-based SNARKs on Ethereum. There's a few flavors of pairing-based SNARKs. There's Groth16, which I think probably a lot of people have heard of. It's very cheap, it's very small, it's very efficient. And then there's Plonkish KZG, which is basically like I would say more modern version of Groth16. This has a circuit-specific trusted setup. So if you want to do a particular computation or a particular circuit, you have to do a circuit-specific trusted setup for it. For Plonkish KZG, there's a universal trusted setup. So you do it once, and then you can just use it over and over again, no matter the computation. So for us, we use Plonkish KZG, but we can also, we use a proof system called SNARK for this part, and they have both Plonkish KZG and Groth16 as options. But we use Plonkish KZG just because it doesn't have the trusted setup, which I think is like kind of bad for like security reasons, and also it's just annoying to do.
Got it. So back here, we were talking about it's like Fry, and it uses lookup, and it's a Stark and error constraints, and this is like a whole different kind of set of cryptography tools. And then when you get over here, you need a different set of tools. Instead of small fields, you have large fields, and instead of like maybe hash-based commitments, you have like pairing-based commitments.
Yeah, exactly. And so basically, to recurse the Stark into a SNARK, we wrote a circuit in a SNARK world that verifies this Stark. So we wrote a Fry verification circuit, and then we get a Plonkish KZG proof out at the end, and then we verify that on Ethereum.
Right, so you have yet another circuit. You had like at the bottom, you had your CPU circuit, and then you had one that combines Starks, and now you have one that takes a Stark in a SNARK, so you can verify it on EVM.
Yes. So yeah, that's the whole pipeline.
And this is hundreds of kilobytes, and this is what?
In practice, this ends up being like very, very small. Like it ends up being, 3 elliptic curve points, so it's like hundreds of bytes maybe.
Okay, cool. And then this is millions of gas, and this is maybe like a few 100,000.
Yeah, it's like 200K, 300K gas.
Yeah, that's awesome. Thanks for showing me this. I think I get it, how whole zkVM works at this point. Maybe one more thing we could cover is like, what are these good for? Like, what's the point of this whole thing?
Yeah, totally. So I think ZK has a lot of use cases, but a big use case of ZK is privacy in blockchains and also scaling blockchains. So things like ZK rollups, for example, are kind of the future of Ethereum scaling. And I kind of described this earlier. You have a bunch of transactions. You generate a ZK proof that the transactions were properly applied to some, state, and then you get a state root. You post that on Ethereum, and then you can basically lock ETH in a bridge contract, and then, do a bunch of transactions off-chain and generate a ZK proof of, what everyone's updated balances are, and then later you can use that to unlock the ETH. And so that's kind of how a ZK rollup works very quickly. And I think, Vitalik has said many times that he thinks the endgame of Ethereum is like everyone's going to be transacting on a ZK rollup. Now, historically, to make a ZK rollup, you needed a team of like 30 people, 30 very smart cryptography PhDs who hand wrote a circuit for the ZK EVM. So Ethereum has the EVM, Ethereum Virtual Machine, and people write Solidity and they write smart contracts that compile to EVM. And then you needed to write the circuit that has all the logic for transaction processing and running the EVM and stuff like that. And it was very complicated. It took many, many years, and it was very difficult. And there's a lot of other downsides, like it's hard to audit and understand what's going on, and it's hard to like customize and upgrade and modify. With the zkVM, what you can do is you can take an existing Rust node of Ethereum. So for example, something like Ref. It is a Rust implementation of an Ethereum client. So you can just take Reth's transaction processing logic, Reth's EVM, things like that, and you can just import it into a zkVM, and you can run Rust code in your zkVM, and now it becomes like kind of a weekend project to make a zk rollup. So now making a zk rollup is really easily accessible to many, many more teams. It's much more maintainable. It's much more upgradable. Remember, like Ethereum hard forks every 6 months to 1 year. So every time there's an upgrade, you're just, let's cargo update my version of Reth, and then, oh, I'm now still compatible with Ethereum. And so it becomes like much more maintainable, much easier, etc. With our zkVM to have zk rollups. And in general, there's like a lot of use cases in crypto for zk, including zk bridges, categories like zk coprocessors, things like zk oracles. And historically, all of that's been very, very difficult to do because you need very specialized expertise to write zk circuits and do all this complicated stuff. In the zkVM paradigm, now any developer can just use zk by writing normal Rust. And then underneath the hood, a zkVM team will take care of all the hard stuff for you. They'll worry about recursion. They'll worry about SNARK to SNARK. They'll worry about all these constraints. But you as a developer, you can use zk by just writing normal code. And that's why zkVMs are awesome. It just makes zk really easy.
I see. I guess it comes with some trade-offs because like the zk EVM is this custom built thing, and the zkVM can do kind of any Rust program. So I guess it takes longer to compute maybe, or what are the trade-offs there?
Yeah, the trade-offs are that, there is more overhead. So, the proof time can be a bit slower. But in practice, actually, we've found that because the zkVM is really general, so like it's really general, you can support a wide variety of use cases, it can support a wide variety of teams, you can really put in the work to optimize it in a way that one specific team who's only doing a specialized circuit, there's not as much engineering ROI to really optimize it. So basically, with the zkVM, we've actually found for a lot of use cases that it can be more efficient than an unoptimized circuit-based system because we have like a team of very competent people working on optimizing it. There's a lot of other teams also working on this problem. And because it's so broad, there's a lot of ROI to making our VM more efficient. So there are trade-offs. It is like a little less efficient. In theory, it's a lot less efficient, but then in practice, you're kind of able to close that gap just because engineering is difficult. And if you're working on improving one system that many people use, it's kind of easier to improve.
Got it. Okay, cool. Well, thanks for joining us. Thanks, Uma, for sharing how zkVMs work. It's complicated, but cool. I think it's been a great overview. So thanks for spending the time with us.
Yeah, thanks for having me.